Okay, I am attempting to get this going again. Oh, technology. Okay, we're going to give everybody just a minute here because the other stream, I pushed a button I wasn't supposed to push. Because why not? Give everybody just a minute. Alright, so I'll probably end up deleting the whole first section of the other one, and I'll restart my thought here for where I left off. Thankfully, I wasn't very far into the stream. Don't push that button. Got it. So, one of the ideas I've had that I haven't really pursued is actually pulling up a procedure, like the PDF of it, and reading through that procedure, and then doing a discussion, interpretive dialogue about it, for example. Because there's a lot of ways that they say things or they do things inside of those procedures that doesn't always translate, or it's not overly clear, not without significant or adequate background education, experience, understanding. There's ways that they say things and the way they term different stuff that if you don't know any better, like you're not going to it's going to be hard to understand it, which is one of the big feedbacks I've gotten from a lot of young technicians is just this makes no sense, but yet somebody like myself or another senior tech can sit, read it, and break it down further. That's that education and experience aspect coming in, being able to interpret what the manufacturer is saying in that procedure. So it's an idea I've had, right? And it's something I've played around with in my head. I've never actually taken the time to do anything with it. So I don't know. It's just an idea, right? And I'm sorry for the stream mix up. I pushed a button apparently, and so I had to. I can't, once I end it by mistake or not, I can't go back into it. So I just have to completely start over. So I apologize for that. Any confusion? I've got a little beetle here wanting to come join the stream, right on the microphone. You go somewhere else. Where do you go? There you go. One second. Let me deal with my beetle friend here. We are truly live, if you didn't know. Like, this is not a pre-recording, so can't make some of this stuff up. Okay. Questions. It's Monday, right? It's Monday. Let's get into it. Start of a fresh week. Killed the live stream partway through my intro. Beatles walking on the microphones. Yeah. Anyway, what is so on the if you caught enough of it to make sense of what I was saying about the procedures thing, I would actually like some feedback on that. Is literally say pulling up some service procedures and reading through that and having a discussion around it, is that actually interesting, or would that be helpful? um, the One of the struggles I have with trying to do like step-by-step procedures in a video format, even if I was in front of the equipment, this is something that really frustrated me over time as well. When I didn't have the written procedure, it's hard to say follow and act out the video form when I don't have the written to reference and be able to kind of read in detail, right? And that may be just a me thing. I'm not sure, but I would really like some of that feedback because that is kind of judging how I'm trying to approach things in the moment between the service program and doing these live streams and such, and kind of like what combination of this really brings the most value to you, because that is my ultimate goal. Like, I want this to actually be useful and helpful. It's not just me taking a couple hours to talk because I'm full of air. So, yeah, just any thoughts on that? That'd be really helpful. Okay, so let's go. If you have a question, feel free to go ahead and get those in. Please explain CVH control diagram and panel. Do I have a diagram I could pull up really fast? Ooh, I should actually. I should. Okay, let's go do some exploring. And it kind of depends on CVH. So actually, to clarify that, are we talking a CVH like UPC2 series panel? Or are we talking a CVH like I would assume you may mean the more modern, which would be the CH530, the little green touch screen, or the the UC control panel, which is the color graphic display, right? So those control panel diagrams compared to a the UPC 1 and 2, quite a bit different. So it is important to distinguish which one of those two, because it's like very different control systems here. Um, I think I might. No, I don't. I don't have a fast. I don't have a fast grab of the newer series that I could just pull up real quick. It would take me a minute to get all that loaded up. I don't want to kill that much time for the stream. If we were talking about the older panel, I know I've got one of those set aside. Yeah, we'll come back to that. If you have any questions, go ahead and get them in. I will pull one of mine that I have on standby. So in the future, if you're watching this after the fact or you have a question that comes up after the fact, feel free to get those into the comments, and I'm getting those saved in a separate place so that I can refer to them later, like now, and we can have a discussion around it. Okay. So this was one of the questions that has come up recently. How many tubes is too much? When too many tubes are compromised, what do you do? I saw CVHE last week with about 20 to 30% of the tubes on the condenser barrel plugged. So by how many tubes is too much? So this is going back to, we have a set of condenser tubes that are leaking. They've been diagnosed, whether it be low pressure, high pressure machine, doesn't really matter. And this is not just for the condenser side, but this could be true for evaporator or condenser side. So just depending on the circumstances. My personal training that I've come up understanding is usually somewhere about 15-20%, maybe even as low as 10% on some machines. Just kind of depends on your circumstances, but somewhere in that range, you will start to see pretty significant heat exchange degradation. Okay, now if that means it's on your evaporator side and you've had to plug a bunch of tubes there, well, then you're going to be running much higher approach values. You're going to be struggling to make leaving water set point without pushing your evaporator saturation down too far. So that would be a symptom, right? The condenser side, you're going to have just the opposite. You're going to start running higher approaches still, but you're much higher head pressure, which is going to push your lift higher if you're dealing with a centrifugal. So with a centrifugal application, one of the struggles is you're really going to start driving those lifts. And if you're already in a condition where you've had trouble with this machine and maintaining staying out of a surge and keeping the lift under control, you start having to plug tubes, you reduce that heat exchange. Like that snowball effect really starts to catch up to you quickly there. So The first few tubes you do, you're probably not going to notice much of a difference. And in fact, I'm pretty sure the manufacturers take into account some kind of like failure percentage. And so as long as you don't lose X number of tubes, if there's a noticeable difference, it'll be a very minor efficiency loss, but it won't be a significant like operational performance loss, if you will. Um, but by the time you're hitting that 15%, give or take, 5% mark for a lot of the machines, you're really going to start noticing it. So in your particular case, with 20 to 30% of the tubes being plugged, um, yeah, I would expect that machine to run pretty significant condenser approaches, and brushing the tubes isn't going to fix that. That may be why you're in there trying to brush the tubes. You may have had higher approach. You may have been struggling with high head pressure. The default there is, okay, well, maybe our tubes are plugged up or dirty otherwise. So you go in there to brush them, but then you see a whole bunch of them are plugged, right? Immediate red flags. Now, then the question becomes what's going on in this particular loop that we're having that many tubes need to get plugged in the first place? Are we having a water side issue? Are we too high on our GPM? Are we not? Is the chemical balance not correct, and we're starting to heavily corrode the pipes themselves? Like, what other conditions are possibly going on that could be causing um, the tubes uh, to need to be plugged so often? Okay, so those are some things, or that is what my training is on kind of that breakover point. And so typically what I've done is I'll just push that machine up to that limit. And when I get to the point where the condition is just too severe, right? What I mean by condition is we're having trouble maintaining stable operation because we just can't exchange enough heat through those tubes. It's time to consider either doing a retube, which would be a pretty common next step, right? And now, depending on your machine, maybe you could consider an overhaul condition at that point. Just depends on the circumstances, right? That's very, very situational. But retubing would be the next simplest step, and having a company come in, or your company if you do it in house, remove those old tubes, install new ones, flare them out on the end plates, and then you basically you've got a whole new set of tubes, and then you can get back into normal operation at that point. Now, depending on your circumstances, it could be a situation where it's worth considering just an all-out replacement. If you've got an extremely old machine, and especially from an efficiency standpoint, this machine is just they just ain't cutting it anymore. It may be worth, instead of trying to pay for a really expensive retube, just go ahead and replace the machine, or plan to do that. And at least at that point, if you can get it to run and still maintain some kind of operation, but it hadn't completely failed, then it gives you opportunity to address that chiller um, before a complete failure happens. Meaning, get it ordered, get it replaced. It takes a lot of time to get a new chiller in and to go through all the coordination required to do a chiller change out. That's not a small process. So, yeah, just things to consider. So if you've got a fairly old machine and its efficiency is just not up to par at this point, then instead of considering the reed tube, it may be worth really investing in just a new machine all outright. Anyway, I like the question though. What's next? What do we got next? How is everybody doing? And by the way, if you're confused at all about the multiple stream thing, I pushed some wrong buttons by mistake early on, messed some stuff up. So I am in the process of, or we're on this one now. The other one is no. I'll deal with that one later. Um, so yeah, just in case you're just joining in and you're confused because there was two. I'm sorry. All right. Do we have another question? or do we just have something we want to talk about? Okay, we can go a lot of directions with this stream. The point of the topic is to kind of give us some kind of direction to go with if we had a lot of activity going on. If we don't, like, we can go any direction you want with it. Absolutely. Got another one. Okay. So, this another one is another backlog question that come up. Come on. Me and technology gonna fight today. I can already tell. All right. Hey guys, I have a question. So if you open a motor and the failed bearing have seal on both ends, should I take one side seal off of the new bearing before install? Now this is in the context of a standard motor. It could be a pump motor, could be, a open drive motor like we see with a YK. Sometimes we'll do those bearing change outs in the field. I've had to do that before. So if we're going to be doing a bearing change out like that, what do we do? So the bearings themselves will have they have shields on them. Okay, so in your particular case, if there's a difference between sealed and shields. Okay, shields don't have any kind of sealing material or anything around the edges of the race, where a sealed bearing will. It looks different on the race itself, and it should be identified like on the bearing packaging. So even if the original motor was truly a sealed bearing, okay, even if it was, as long as you have a grease housing and grease ports that you can grease the motor with, converting that to a greased bearing or a standard bearing isn't going to be a problem in my experience. I've had to do that plenty of times. Those sealed bearings, while they're great in theory, depending on what they're being connected to, if you've got a lot of heavy loads on that bearing, those sealed bearings tend to wear out fast enough, right? And I'm not saying they can't handle it, but they wear out faster than I would consider a properly greased standard bearing would probably do in that same environment. And I can pull up some pictures here to discuss this a little further. If you give me just a moment. Actually, come on. Yep, and technology gonna fight. Let's go. It's thinking. Dude, come on. Okay. She's not my day, guys, I tell you. Hey, you know what? Let me have the bad Monday, and y'all have the good one. All right? Can we make that agreement? I will make that trade. If my day is rough, but you get to have a better one, I'm down. We'll take this one. Okay, yeah, we'll use this one. So with our bearing, this is not a sealed bearing here, okay? There's no sealing material. This is just a shield. So this is a ball bearing, this is a roller bearing. Majority of our motor bearings are going to be ball bearings. They handle axial loads far better than a roller does. Rollers are really good for your radial loads, your up and down, but they don't take axial loads in and out very well. Ball bearings can't handle as much weight, but they handle axial and radial loads really, really well, which is why the majority of our motors we use are going to be a ball bearing style. So we have our race here. We have our inner race, outer race. We have our balls in there with our shields. So your new bearings will almost always come, or this, if you order them just a standard bearing, they will come with shields. Now you can get them with no shields, but if you're installing them into let's stick with a simple example of a pump motor. Okay, if you're installing these into a pump motor, then you're going to want to get them with shields. Okay, don't get the non-shielded. And in that particular case, you'll want one shield to be removed, and it'll be the outer side. So if this was our rotor and stator here in the middle between these two bearings, just follow along with me if you can, then this outer side is where our grease housing is going to typically be. And we'll have a grease port out here, we'll have a grease port in the back, and then there'll be this little chamber right here on either end on the outer side of each of these bearings in order to grease that or to grease the bearings to the motor. And what's good about having the shield on the interior side is that as this grease does what it's supposed to do, it's going to sit in here. As it warms up, it begins to liquefy. As it liquefies, it's able to get in and maintain bearing temperature while keeping the bearing cool at the same time, or keeping it lubricated. So it helps us maintain temp and lubrication. And that shield on the backside helps keep that fluid grease from just getting slung everywhere, which is why if you have a set of bearings with busted shields, then the interior of the motor is going to be just coated in heavy grease residue, which will eventually lead to a premature failure due to that heavy grease. It's going to start stacking heat because the air moving through the stator can't reject the heat properly, so the stator is going to run hotter. It's going to break down the insulation faster. Then the grease is going to allow some conductance through it into making the stator short out sooner than later, or even possibly short to ground where it may have just done an internal short, right? So lots of bad things can happen when we've got busted shields. So in that particular case, I just use a little small like screwdriver. It doesn't take much, but you'll just pop one shield out. You'll try to get underneath the shield, in between the shield and the race, and just kind of ping it out. Remove one side, leave the other, and then the shielded side is going to be in towards your motor and your stator and the rotor, right? And then the non-shielded side is typically going to be your outer side, and that's where the grease is going to come in from the grease housing. So if you are if you're replacing some motor bearings and that's your circumstances, even if they are like if they're truly a sealed bearing, then you don't need to remove the shields whatsoever. Like, just, it's a sealed bearing, leave it be. Just remove the old ones, install the new ones. But if they're not actually sealed and they're just a standard bearing, that's when you want to remove those shields, but not both of them. And then if by mistake you got a set in that were non-shielded at all and it was open on both sides, please don't install that. It was a mistake. And you want to make sure that, like, the bearing shops I've worked with, or the motor shops, like, if that happens, which it does on occasion, you get them in, you need to look at them when you receive them. Don't just walk out the store. Make sure that they actually have the shields on them and that the right thing actually came in. Because if it didn't, you can handle it right there and say, no, I'm sorry, I needed shielded bearings here. Not sealed, shielded. Okay, these are race shields. So at that point, you can just get them exchanged. Obviously, that's going to probably cause some delays if you had to order them in the first place. But like, that would be the process there. Don't install non-shielded bearings in a motor like that. You will just make a complete mess of everything, especially that motor stator, and that will cause a premature failure because all of those are air cooled, which is why they've got the little fan mechanisms and stuff, whether internal or external, however they're doing it. All of those are air cooled, and that grease becomes an insulator, just like oil in the refrigerant circuit coating the tubes becomes an insulator to the tube and causes approach issues and heat exchange, right? Well, that grease will do the same thing to our motor, will cause our motor temperature to rise. Heat is what breaks down our motor insulations. So if that insulation is getting too hot, it's breaking down faster, and you've significantly shortened the lifespan of that electric motor versus, if none of this had happened and it was nice and clean and protected. Anyway, can you explain water pressure standard in the chiller? All right. Can you explain water pressure standard in the chiller? So by water pressure standard, I'm going to take the approach of, we could go two ways with this, right? We could either go your DP, or we could go with your actual physical pressure of say the loop pressure. I'm going to start with DP here, and I actually have a service procedure I wrote on this to help kind of walk you through this process for trying to determine what your DP should be. Because ultimately, if we're trying to measure flow, then using DP, differential pressure, okay, so your inlet and leaving pressure on the water side, the difference between there is your flow DP, or your heat exchanger DP, and this is true for evaporator or condenser. So you'll take that DP, and that gives you a reference. Now, this is something we have to be careful with DP, is it's not the, Boyle's law, I think, where like with a valve or a strainer, the more pressure drop you have across a strainer, the less flow that strainer actually has. This is actually a reverse condition when it comes to a heat exchanger. The more differential pressure you have across the heat exchanger, the more GPM you will have. So that's an important distinction right up front. So if we want more GPM, we need a higher DP. And this is a separate deal from, say, like a strainer or a valve, something like that, where like two different principles here. So most, or let me rephrase, not even most. If you can get access to the manufacturer's flow data for that particular machine, great. Okay, and then that's a very default answer, and let me talk that through a little bit further. In some cases, you're going to use the IOM, the Install, Operation, and Maintenance Manual. Okay, that will give you the information you're looking for in order to get the flow specs for that heat exchanger, and it'll be the heat exchanger specifically. So what they'll have in there is they'll have a chart, and it may have a few different heat exchanger models. Maybe. Sometimes they don't. Sometimes it's just one default chart for the majority of their heat. You'll just have to see how the manual's laid out to what they recommend, right? So to find out that heat exchanger code, you'll just look at the nomenclature breakdown, which will typically be at the very beginning of that IOM manual. And somewhere in that nomenclature sequence will be a couple of digits that indicate the heat exchanger's code. All right, so that is what the manufacturer knows. Okay, basically that's the heat exchanger model, if you will. And all of those numbers get compiled into one string of what is the chiller's model. So you need to, you'll take that, reference the manufacturer material, and then identify which flow curve is right. Now that could be in the IOM, that could be in the engineering manuals. So most of these chillers will have a operations and maintenance manual, IOM, and then they'll have a separate engineering manual. And some engineering manuals will have those are the manuals they're using to actually like design spec machines with customers. So if you're trying to determine what your flow is, then you may be able to go into there, find that model, using the digits in the model number, and then you can reference what your flow should be. Now, one of the issues with that is not all of those are going to be accurate or they're not going to give you an actual DP value. In some cases, they may give you a GPM value, but it won't be a flow like a DP. Like you should have this DP. It'll just be you get like this heat exchanger can do between X and Y GPM. Like that's what it's rated for, or it's capable of doing. So in that particular case, let me make sure I'm getting notifications that my internet is not jiving today, because why not? In the particular case where you don't have the DP value, then none of that information is helpful whatsoever. Okay? So at that point, your IOM is useless and your engineering manual is useless as well. There's not a whole lot you can do. So the only other alternative, or let me rephrase, another alternative is you can get the actual sales information for that machine and what it was spec'd for. Technically, the customer should have that on file somewhere. Sometimes the startup technician will write that in the panel. So inside of the control panel, he may write what the design DP is and GPM and like what all that data is. He may actually do that, and that would be really helpful if everybody did that. But my experience is that you'll get that sometimes, but even then, there's been times where what was written in the panel wasn't correct. Like I later got the actual submittal for that chiller, and it was not what was written in the panel. So you have to be careful with stuff like that, because sometimes people will think maybe they didn't have the actual factory data, but they think they had, or they figured something out, and like, okay, well, this will work, so I'm going to write this down so the next guy knows that I may not have the actual data, but I knew this worked, even though how he made it work may not be correct whatsoever. So that would be a second way. First way, the manuals. When that doesn't work, we have the submittal data if you can get it. Okay, that's the other problem. Sometimes it takes a while to even get that back from the manufacturer if the customer doesn't already have it, or you may not get it at all. So depending on your circumstances, that was typically my experience. Trying to get that submittal form was very challenging without actually contacting people I knew who could get that information for me, right? If I couldn't do that, getting it sometimes just wasn't on the table. So then you're left trying to operate with just no information at all. As a last case, worst case, I can't get anything, but I need a starting point. Just something to start with. And I'm summarizing my procedure here, by the way. So like what I'm talking through, this is what is in my service procedure in the academy, in the service training program. Using the number of passes on the heat exchanger can be used as a starting point. I'm going to very carefully say this, because this should not be your default go-to when it comes to trying to determine flow. But in a lot of circumstances, a fairly consistent DP you will have, especially on the smaller tonnages. Now, as this scales to larger equipment, these numbers they mean a lot less as you start getting, 200 or 2,000 tons and above, right? It changes a lot. Anyway, 2 to 4 PSID per pass is a get you in the ballpark type of number. So if you've got a 2-pass machine, one way to know that, do both pipes leave out the same side? Yes, 2-pass, okay? So if that is true, then a 4 to 8 DP would, again, get you in the ballpark. Now, you'll have to use the chiller's operating data and a whole bunch of other information to try to determine, am I operating okay? You may still have a lot of symptoms even kind of getting in that ballpark. So you'll just have to work through that to see in the field, okay, what can I do here? But it at least gets you an idea, and you know that if you're way the hell outside of that, then you're it's just not, you know that something, unless you've got a special case scenario, something's not right there, right? Now, if another thing I want you to be careful with, if you're dealing with some of the manufacturer submittal data, like York as a prime example, if you get to the sales order screen and it's filled out, sometimes they're not. I've had that. So if you get to the sales order screen, it's not going to give you PSID. It's going to give you, feet of head. So you have to convert that, which is, oh shoot, what was that? 2.31 PSI per foot. So if you had 14 or 15 feet of head, you would divide that by 2.31, and then that would give you what your DP is. So they want to see, say, 15 feet of head differential between your entering water and leaving water. You can convert that to PSID, and then that'll be what you set to. Now that's if you're trying to determine DP, okay, in this particular question. If you're trying to go from just a loop pressure perspective, that comes back to your actual elevation. Now, there are going to be some special circumstances where they have higher pressures than what your normal calculation would be for that application, okay? That becomes very specific. But in most of your general purpose plants, I'm going to say it that way, so it could be used on a variety of things, that's going to be based off your elevation. So we want to make sure that at the top of our loop, we are full of water with a little extra headroom. And if we make sure that we have enough water, then we're not going to have issues with cavitation and things at the pumps, which is, literally air being pulled apart and separated from the water, which then creates air pockets without actually having a leak, right? So you cavitate bad enough, not only will you tear the pump up, but you'll end up, like, you can have air pockets begin to build in different spots in your loop. Not a good thing. And your chillers tend to be really good air traps, by the way. I don't know if you've ever noticed that, but they work pretty freaking well when it comes to trapping air. So anyway, for every foot of elevation, you're going to have, for every 2.3 feet of elevation, you're going to have about 1 PSID. So you want to get to a neutral point, right? So if I've got a 10-story floor, and now a roof is counted as a story, right? So if you've got a chiller on the ground level and your air handlers are on the roof, then you've got a 2-story setup there, not a single story. If maybe just one single story on the main level, but you have to count that roof as an additional story when it comes to the calculations we're going to run. So either way, not the best in mental math here, but you're going to take the feet elevation of what each story is, which in most commercial settings, 15 feet is pretty, give or take 5 foot. There, some are significantly more, some are less. Some, like the first floor, may be super tall. The rest of the floors are much lower down. So you just have to calculate that in. But it's based off of that elevation. How high up, which the height of your stories gives you an indication. So what you'll see is at the bottom of the loop, the pressure increases as the height increases. Even though at the top of the loop, we may still be at 0 PSI up here. As we increase height, we'll get to the point where down here we may be at 50, 60, 70 PSI at the base of the loop, the bottom, but still be at 0 PSI at the top. Now, if you are in a situation where your loop is running that low of a pressure at the top of the loop, you technically are pretty low on water by my standards, And I'm basing this off of the return side, the side coming back to the pump and the chiller, right? So I'm using that pipe as my standard with the pump online. So with that low of a pressure, you risk the cavitation, because once you start pulling the water down below 0 psi or close to 0 psi, that's when cavitation can start to happen. So even though at the pump itself, and I go over this in much better detail and structure in the introduction or in the certification course. So if you are enrolled in that, I would suggest kind of go back and review that a little bit. But just kind of ad hoc here. Even though you may have higher pressure at the pump, because the loop actual volume is insufficient, you can still create a cavitation issue, even though technically you've got 50 psi coming into the pump. And that's strictly just because of elevation. It's not because there's actually adequate water volume. So what I like to do is, once I get that elevation psi that I know that I need, I personally like to add 8 to 10 psi of pressure over that on my return or my suction pipe coming back to the pump, above that zero. And I like to have at the very top of my loop about 8 to 10 psi of positive pressure with the system online and running. When I have that, then, like, for me, that's a gauge to say I've got adequate water. Now, it doesn't matter if my pump was on the roof. It doesn't matter if my pump was halfway down the building. It doesn't matter if it was down in the basement. That is irrelevant. What matters is what the pressure is to the actual height of the loop. That will determine what our actual loop pressure is going to be. And this is true for condenser water. This is true for chill water. One of the things you have to caveat here is, if you have an open loop tower on the roof, but several stories down, like this, the open loop tower does change things a little bit, because we have an open loop system. We can't pressurize it the same way we can with pipes. But because it's open loop, we don't have those same cavitation issues. Things change a little bit because there is some give and play without forcing the water into a cavitation state with an open loop system. Whereas with a closed loop, because there is no, other than the bladder tank, there's not as much breathing space, we can actually make that water begin to cavitate if we do not keep enough pressure at the top of the loop, which is where I recommend that 8 to 10 psi over on a closed loop application. So yeah, either direction you were going to go with that question, I hope that helps. And it's a very important topic that I really see that a lot of people struggle with. Understandably so. It's not overly explained well enough, in my opinion, throughout the industry. And there's a lot of, like, I've hear all the time, you ask me, well, what's your loop pressure need to be in that plant? Oh, I mean, loops are supposed to be 35 psi or whatever. And that's just, no, you have to take into account your elevation changes, and that elevation is going to change your head pressure, in addition to just where the pumps and equipment is located inside of that loop. That has everything to do with what pressures and such you actually require. So, Christian, do I work on industrial ammonia systems? I do not. So I don't have any formal training or anything on that. Differ as far as pay and difficulty from chillers. Yeah, so from what I understand, I know ammonia techs, especially skilled ones, can do extremely well, and I would say it's very comparable to working on chiller systems. But I don't have the proper background or knowledge or anything to actually comment on that. So I'm not the best resource there, right? Or not even a resource really. So I would If anybody is familiar with the ammonia space, feel free to jump in the comments and help Christian out. But I personally do not know. Okay. And I do see my signal is kind of dipping in and out here, so I'm sure on y'all's end it gets choppy. I apologize. These questions and stuff, I do have the separate recording going. So if there's some critical parts here in each of these responses that you really didn't want to miss, I will get these edited and re-uploaded in their individual parts, so you don't have to go through the whole stream and such. So just, yeah, in case that gets annoying, I'm just letting you know that I will get all that addressed on the back end. Okay, we've got plenty of time. If y'all want to get some more questions in, I am currently working on some backlog questions. So feel free, and they don't have to be over our specific topic. I just want to put that out there. They can be over whatever questions you have. Okay, that is perfectly fine. Let's see. All right. Got another one in the log. Let's pull this one up. This one's going to be a pretty technical answer. Okay. Yeah. I'm sorry, Hussein. Me and technology. If you've we've been fighting all morning, so I apologize. I will get these uploaded, bud. All right. Dive into this question here. I understand surge condition here is a pressure ratio too high or discharge pressure out of envelope. I am familiar with turbocore compressors where surge speed is lower speed instead. Why is this difference? Am I missing something? No. What you're seeing is the surge graph or the surge curve represented in a slightly different way. So in some of the graphs that I've shown in the past, my little homemade one, it depends on which graph you're pulling up. So in my graph, I'm showing lift versus flow, but in other graphs, you can see it as actual speed. Okay, so let's pull up an actual turbo core schematic here, or not schematic, but the interface. And let's talk about it from this perspective. So this is the SMT tool from TurboCore. And what's being referenced here is the choke speed, actual, and surge speed. And you'll notice the surge speed is lower than the choke speed. And okay, so why is that? Well, all of this, like the choke and surge values are being based off of this pressure ratio up here, which this is compression ratio. All right, they just reference it as pressure. So this pressure ratio, which is it's dividing the suction pressure from the discharge pressure. Okay, the ratio between these two gives us our where we're at in our surge curve, which is the lift compared to the flow. Now, another way to say flow is speed. All right. So speed is another term we could use instead of saying flow. Now, the reason that the surge is lower is because these set points are dictated based off of this ratio. So as this ratio increases, this speed thresholds will increase. And as this ratio decreases, these speed thresholds will decrease. And so this will be a constantly fluctuating point based off of this pressure ratio. Now, and I don't want to oversimplify this. I'm sure that Danfoss is probably going a little bit deeper than what I'm actually explaining here, but my goal here is to give the basic core concept of how they're dictating what these speeds should be and what these speeds mean in relation to surging. So one of the things that why this surge is lower RPM is because if our pressure ratio remains the same and constant at 1.7, but we lower our speed too much, then what we have done is we have pushed over into our surge line. Okay? And let me do something here, because we need to kind of toggle back and forth. Give me 1 second. Let me pull up my actual little graph I've made to represent this. Okay, so bink, got it. So that's right. 1 more second. I need to add one thing, because I really want to help make this more clear. Okay. Just give me 1 second. Let me manipulate some of this stuff around. There we go. Push buttons. Things happen. Okay. So in this particular case, this is another way of representing that, right? So we have lift and then we have flow. So your pressure ratio is on this side, your RPM, say, down here. So if we're running at this RPM with this lift, where we line up right here on the graph, and our lift doesn't decrease, but we slow down, meaning we have less flow, then we move straight over to this point on the graph. And then we push, we're beyond what our surge line is. So lower RPM pushes us into a surge, okay? Whereas in the same way, choke is where so with a surge condition, we overcome how much lift the compressor can handle, which then means that our refrigerant can literally reverse flow and backfeed through the impeller. Very, very bad condition, hard on the bearings. Choke, on the other hand, is where we're not actually feeding the compressor to a point where it can keep up. So I'm trying to articulate it better. I'm not as proficient as articulating choke as I am some of these others. So with choke, essentially I think of it as the compressor or the impeller is getting starved. It's trying to flow more than it can based off of the lift conditions, which creates its own type of, I don't want to say like a cavitate, because cavitation is not right, but it creates its own stability issue. I'll say it that way. So in reference to our turbo core here, so if we have surge speed, if the actual speed lowers below this surge speed, meaning that we came over here and we just moved straight to the left of this graph without actually reducing lift, which can happen, then we push into a surge state. Versus if we increase speed without adjusting our lift, depending on where we're at here, you just follow the example. If we increase speed without increasing our lift, then we have the potential to push over into a choke condition. So we want to float right in here in this zone between surge and choke. Like, this is our happy spot, if you will. And that's what's being represented via these speeds. We're just doing it in a different way. And that's the thing to keep in mind as to, okay, if you're familiar with the SMT tool with turbo core and how these values are, this is just another way of saying flow is how I would represent it. Replace speed and RPM with just flow and CFM, and you accomplish the same basic terms with our ratio being just our lift. So instead of saying lift in terms of, say, saturation temperature, so we have 45 degrees of lift, we're using it in terms of ratio and the ratio between suction and discharge. Okay, so this ratio helps us determine where we are on this actual graph over here on the left side. So where we're at here on this graph, where our PM is, like these, it's just two ways of saying the same basic thing. Is how I would characterize it. All right. So no, you're not necessarily missing something. It's just a different way of representing the data. It does go back into having a deeper fundamental understanding of that surge graph and what that curve means in relation to the compressor. So, yeah, hope that helps. Let's see. Yeah, I appreciate it, Hussein. It's one of those days. Like I said, I'll take the bad Monday. You'll take the good Monday. I'll take the bad one. We'll be all right. I'm currently at Light Commercial Tech Southeast Michigan. Our company dabbles in a little bit into controls and heavy commercial, but no water cooled chillers. Oh, okay. Yeah, well, that's pretty common, Christian. Starting off especially in the lighter side of the chiller world, and especially air cooled equipment, like those things are typically the easiest accounts to get started in, especially if you're trying to move into more of a chiller side, heavy industrial or heavy commercial, pushing into industrial type of environment. Like that's a good place to cut your teeth and prove to the market that you are a company and you have a team that is up to that challenge. It's a very, very common way of a company to build that reputation and then scale into larger water-cooled equipment as they go, which is a whole nother beast compared to an air-cooled system. Like a lot of the same fundamentals, but very, very different in terms of controls and maintenance and such. And equipment that you'll need to do that effectively, because then you start getting into low-pressure equipment, which, again, just you need different equipment for that, like a pressurizer. So you have to replace service pumps, pneumatic DDC actuators for dampers and valves, etc. I know, very basic. Chillers from your videos. I'm currently making 40. Thinking of either starting a light commercial, mainly servicing, or moving and working to another company servicing heavy commercial. Do you have any advice as to how long it takes to learn the heavier side of things and how much I might see a jump in pay? Thanks. The really difficult part to the pay conversation, I find, is it's so it varies so broadly depending on where you are and the cost of living in that area. So yeah, I don't have, in terms of pay jump, if you're not already working as a standard, let me say it this way. If you're not already working in the chiller side and you don't already have like that as part of your repertoire, but you want to get there, I have not seen an environment where experienced quality chiller techs are the most paid guys, period. In any team and setting. Like that is those are your that equipment alone is the highest revenue in my experience. We can push the margins. We have much larger jobs, and like part of one way to think about your income is it's value to the company. Now, not everybody is fair in this, okay? So some companies just flat out screw you over, and that's on them. And it's up to us to be mindful of that and try to make better decisions on who we want to work for. And you're in an environment right now or nationally across the US, like you have a lot of sway in who you want to work for as long as you have a good foundation yourself. So the more value you can bring into the company and that you can show, like the revenue that you're able to produce, the more you can advocate for higher pay scales for yourself. So like if you can be that, if you can get to that stage where you're doing 750 to $1 million plus as a technician, and that's gross sales. And I say sales as in you're doing the work that is you're doing projects and work that is bringing that kind of revenue in. Then you have a lot of standing to really press for much higher earnings within the company, because well, you're bringing in, or you're enabling the company to do work at that level. Like I still always say it, even if you're not the technician selling that work, they have salesmen, or this is something coming in from customers. If someone like yourself wasn't there able to perform that level of work at that value, then the company would not be able to maintain that type of high revenue, right? So this is a way of just kind of thinking about how your value to the company can be used or leveraged to increase your own earnings. And I'm saying this even from like I used to be an ops manager. That's what I did for a couple of years before I stepped out of the field. And like this is one way to evaluate what's the best path. Is the people who are your highest revenue earners, even if they're not selling the literal jobs, they're not speccing the jobs. A salesman is, and most of the time they're paid on commission and such anyway. But you're the one who's the primary guy to do that work, or one of them. That you deserve your piece of the pie if you get my if that makes sense. So that being said, when you scale into that large of equipment and you're doing that level of work, those are really expensive, high ticket jobs. Just period. Like it's just not, you can't work at that level of equipment and it not be expensive. It's just it costs a lot. And so you can advocate for that. Now that means also getting yourself into that position. So that's one of my missions here, right? I'm trying through Chiller Academy. I am doing my best to build resources to significantly accelerate your ability to learn this information very fast, apply it very fast, and really get it into your core without having to go through what was traditionally years and years and a decade plus of this whole cycle to eventually be determined worthy in this industry. And we've had a lot of success with that, right? I'm not, my goal here is not a sales pitch, but as a means of how can you get and learn this material, like what we're doing here. I mean, this stream is a perfect place to ask these kind of questions and try to expedite your learning process. And ideally, I want you to be able to combine this with actually putting the hands on in the field. So that's the other side of it. If you want to take those steps, but you're with a company who isn't currently working that side of things, I would heavily encourage you to get with a company who is. Like if you want to go chiller side, now if you want to start your own company, that's up to you. I personally knew that I don't want to put my family through owning and operating a service company. I've been a part of that life for too long. My family has sacrificed enough to just get to where I am now. And I don't, starting my own service company only makes them sacrifice even more on a level that I'm just not comfortable with, which is an opportunity for you because it is extremely freaking hard. Um, and if you're in a position to do that and your family's on board with it, then great. But I think that's something to understand going into it. Um, it's the buck stops with you, and it's a lot of financial liability. Like it's a lot. So you've just only you can make that determination on starting your own company. But in an approach where you don't start your own and you want to grow into chiller side heavy more heavily, then you need to be with a company who that is their primary focus. That is what they do routinely, and they've got a reputation and they've got everything built around that. They've got the infrastructure to where you can get in and learn quickly, and ideally have people you can ask questions. So it sounds like if your company isn't really into chillers all that heavily, they're starting to and they're doing a little bit, you've got two paths in front of you. You could either take the flag in your hand, which is something I have done, and it worked out really well for me, and charge forward with saying, hey, I want to do this. I think I can. Let's make us a more premier chiller service shop and drive that flag forward. And that worked out really well for me, but that required a company who was willing to reward me and work with me in part of that process. It's a very difficult thing to do at the same time. It's not easy. If you don't want to do that or you don't feel up to that, then finding a company who already has it, and that's who you want to work for, because then you can start going through the process of getting more hands-on, getting to see what they do, how they bid jobs, how they structure things, how they're doing it, and that will accelerate your process. So and that's really true for anything in this industry. If you want to go a particular direction, you just need to find people who are doing that and then go do that with them and do your best to learn in their environment. And then you can always, as you become better established, move to a different environment, different company, different place. Um, yeah, I would say that there's just so many directions I could go with it. If you're really interested in far more industrial type work, like, so this is where we get into the specifics of what kind of chillers do you want to work on. Are you interested in more data centers? Are you interested in more like industrial manufacturing, comfort cooling systems? Like, all of these are a little bit different specialties, but that does dictate where you want to move. Um, so like where I'm at, we have a lot of industrial equipment. There's a lot of industrial activity. So we have a lot of those systems, as well as a lot of um, like comfort systems. So we have a lot of comfort cooling here. So you got a heavy blend of both. We also have a lot of data centers, but that really rolls into some of your industrial side, but it is a little bit different in how they build their plants compared to a process facility who's got a manufacturing line, right? So there's slight tweaks in that. But if you're in other climates, you may not have near as much comfort cooling, but you could be in a very heavily industrial sector. And so if you're in an industrial sector, you may not be running comfort cooling systems, but you can learn industrial processes being used for chillers or manufacturing plants, right? So these are things to consider and to think about whenever you're choosing if you're going to move, where you might move to, is is there a major need for the chillers to begin with? Because that's some of the feedback I get from some guys is just because of the climate they're in, there's not as many chillers around to begin with, and that's a climate issue. So the opportunities are less. Whereas you go into a place where there's a lot more opportunity. That's what I like about Texas. I mean, we've got a heavy load of all three, especially here in Central Texas. But you could choose any of the major metros here, and there's a lot of heavy commercial industrial opportunity into getting into chiller systems. You got Dallas, Fort Worth, Houston, Austin, San Antonio. Pick just pick one. And there's good companies in every one of those cities. Yeah, that would be. That's my thoughts. We do have a little bit longer if there are some more questions. Any other questions? Give us some more time here. And I see that my stream is still kind of struggling every now and then. I've got some status bars that communicate like how things are going. I apologize for any of the dips. Let's see. This is a, we can do. Okay, let's talk about this one a little bit. This is kind of a we have to be careful. So, how about 10 degrees across evap, but RLA is only at 45%? Now, this is in the context of a machine being loaded or not loaded, or the chiller being loaded or not loaded. And so I've recommended in the past that, basically for a chiller designed for a 10-degree drop across the evaporator, if I am operating at that and I've got about, say, at least an 8 degree or more difference, like I'm making set point and I've got enough, my entering water is high enough to be 8 to 10 degrees, or at least 8 degrees above that, then I consider I've got a pretty decent load, and I should be able to get a pretty good analysis of how the chiller is operating. Now, that is in the context of, I know for sure that my GPM is correct, my refrigerant charge is good, my tubes are good. Like, that's in the context of all these other variables that will impact that differential temperature are in a good state, a good condition. Like, it's very, very important. So if we haven't verified that part, then using the temperature difference across there has a lot less value as a meaning, because if we're flowing too little GPM, like, that's going to completely change things. And we may not have a lot of load, but we'll be able to make 10 degrees really easy, because that water has so much contact time because it's flowing so slowly through the evaporator that we're able to make 10 degrees even though we don't actually have a lot of BTUs flowing through the chiller. Now, another thing I want to address here is you've got 10 degrees, but only 45%. So there's a couple of other things that, let's say all the other conditions are absolutely perfect. Okay, we know that our GPM, our charge, and our tubes, all of that is in good state. We have proper heat transfer. This condition can still happen, and it'd be perfectly normal, where we've got a 10 degree across but only our compressor is only pulling 45% RLA, which would mean that we've got a loaded machine, but yet our motor load is quite low. Well, there's two other things that affect this. It comes down to lowering lift. So I don't have that kind of data, but just things to consider. The lower we can maintain our lift through the across the compressor, and this is true for any compressor, okay? This isn't just a centrifugal thing, but the lower we can maintain that lift, then the less compression we're having to do. And the less compression we have to do means the less work we have to do to still move the same volume of BTUs. So what that could look like is, one, you may be running a higher chill water set point. So instead of 40, 42, 45 degrees, maybe you're running 48 or 50 degrees, depending on your application, or if you've got a temperature reset happening where maybe you've got lower load conditions, or, well, I guess this wouldn't be lower load, but just depending on your circumstances, you may have a higher chill water set point. That particular case, that raises the evaporator pressures and raises the saturation temperatures, which lowers the total lift the compressor is going to have to do. Because of that, we have less actual load on the compressor because we don't have to compress as hard to get to our condenser saturation pressure that we need. Now, the other side of that too is, especially in a water-cooled environment, but even air-cooled ambient, we could significantly reduce our condenser water temperature or allow our condenser head pressure to drop significantly if we're discussing air-cooled. So basically, if instead of allowing the fans to stage to maintain a higher head, we could just allow all the fans to stage on and drop our head significantly. Now, there's oil ramifications and stuff if we're not careful with this, but ultimately, if we get our condenser pressure down and our head pressure down, then again, we have to compress less. It's not as hard to get it from the evaporator to the condenser at the proper saturations. And if you combine both of those together, where you've got a higher evaporator set point and you've got a lower condenser water set point, the two of them are working together to lower that RLA the motor is going to have. So you could still have a technical loaded condition and GPM and all that be fine, but still have a very minimal load on the actual motor of the compressor. And it's just because we're not having to go as far with it. You know, if you're having to compress from 45 degrees of saturation to, say, 70 degrees of saturation versus 45 degrees to 100 degrees of saturation, that is a major difference in how much work that compressor has to do. Major difference, which is going to be reflected in your RLA. So RLA is not a matter of, is this compressor running at maximum load that it could possibly handle. It is how much work is it having to do to flow the volume it's being asked for at this time. That is how I would characterize what RLA is communicating. The compressor may be able to stage up more if it needed to, but if you're making set point, it doesn't need to, but because of our lift conditions, we just may not have it may not require as much work to get it there. So yeah, that would be my assessment if I had a condition where it would be what I would consider fairly loaded, a 10 degree and everything's correct in terms of design specs, but I've only got a 45%. I would say that we've got a full load, but we're managing our lift really, really well. And that is enabling a really low RLA, which is where you're maximizing the cost of performance, the COP. Like, we've got a really good COP at that point, which is all part of why, like, if we, in a water cooled environment, if we can get that head pressure down and keep our condenser water under control, like, we can save a huge amount of efficiency. And I get, there are people who specialize in building optimization, and they're not necessarily mechanical HVAC experts, but they understand envelope, and they're some level engineer, somebody, and they, like, I've had these arguments before where they're trying to sell the customer, the our customer that we're working with, that they need to run higher condenser water set points in order to get the tower fans to not stage up as much and run more efficiently to save energy. What they do in the process, though, is by raising that condenser water set point, yes, we go from pulling 20 amps to 40, 50 amps on the motor, But our chiller in turn goes from doing 100 amps to 150, 200 amps instead, because where we could maintain really low condenser waters and maximize the chiller's efficiency, instead we are forcing the chiller to run at a much less efficient state by having higher condenser water, just so that we can save a few amps on the tower fan. Hope like that. Granted, those of us who have this, like we're on this side of things and we're looking at the bigger picture, that's easy to identify on our side, in my opinion. On their side, again, they're not looking at it from that perspective. So anyway, yes, that is, if you have that condition, that would be my thoughts around that. So parent company owns a large downtown building in Detroit. I always have trouble. I have to sub out chiller controls to other companies, like, because they have technical capabilities. I have a great relationship with my boss, being lead service techs, and I'm thinking about bringing to his attention, tell him that this is something I can start doing. It's easy for us because we already have the customer basis. We're just lacking the technical capabilities. Might be worth having a conversation. Joining. We have a dozen techs that bring in more or less $5 million in sales per year. That's very good. Theoretically, I could definitely have the company pay. Try to cover, yeah. No, absolutely. So, yeah, I did that very thing. Now, I was already say established in my chiller career by that point, but I came on with a company that really wanted to expand their chiller portfolio, but they weren't having a lot of success with it, and so I was at a stage where that's really what I wanted to focus on the most at the time was technically chillers and VRF, but they were really far more focused on the chiller aspect of it. So I just said, hey, just turn me loose. Let me get out there, right? I've got my guardrails. I'm not an actual salesman. I'm a senior tech who's a chiller tech, right? But let me make this happen. And I did, right? And it worked out really, really well. So that is like, if you have a company and a boss that you're on that level with, then just try, right? And if you already have a subcontractor, and I've had to do this, okay, especially in my early years, there were times where I got in over my head, and I didn't really realize how deep I was getting in initially, but I got in over my head, and it resulted in having to bring in outside parties, whether the factory themselves in some cases, or there was some other companies who we were friendly with, who had more experience, who we were able to make phone calls to and have those discussions, right? So you already have a outside vendor who you've worked with who can help you with this. You've got a friendly company, which means that, like, if you just really get off the rails by accident because you just didn't know any better, it may not be good for the company in the short term. It's an expensive bill, but it can, if it works, if you're successful, the upsides of you being successful, in my opinion, are way better than the downsides of you just falling flat on your face, which is probably going to happen a few times. At least it did for me. Maybe you're just the next, Galileo of chillers. I don't know. But I wasn't. I'm not. So I had plenty of mistakes that, it creates tough conversations and scenarios, but yeah, I didn't do that again. I found out you don't do that, and here's why. Really fast. How you doing, Sterling? I see you, bud. You know, does everybody like this 11 o'clock time frame? It's kind of slowly turned into like an 11 to 1, 12:30 to 1 o'clock, somewhere in there, right? So I'd like to start kind of winding down at this point at some point, but I can still take another question or something. Um, I know it's Monday. For me and my schedule, this is kind of what works out best for me versus there are probably other days of the week. And I really, I don't want to make this an evening thing and kind of take that time from my family. So I'm trying to fit this in as best I can with the schedule that I'd like to have. Um, so what I can flexible on is instead of like an 11 o'clock start, 12 o'clock is something I've considered at times. But like if it's not, I don't want to change things for the sake of changing things at this point. Yeah. Well, and that's the struggle I had with trying to choose Mondays in the first place. Is they are so. It is our busy day of the week, and it's. But the more I think about that too, so are Fridays, right? Um, so Mondays and Friday, because Friday we're trying to cram to get things done before the weekend and prep stuff, whereas Monday we're trying to hit the week hard and get the week rolling and stuff. And so it's just so what I could then do, say a Tuesday or a Wednesday stream maybe, and do that around lunchtime. But I don't know, it just everybody also has a slightly different way they like to work and what they would prefer. And so that being the case, like I just don't feel that there's not just like one really easy middle ground. And so I don't know, I'm just kind of rambling at this point. Questions, and it doesn't have to be specific to the topic. I know we're talking about water cooled refrigerant troubleshooting. It doesn't have to be that specific. And is that even? How about this? Is that even that useful to y'all to have something that specific and to vote on it, or does that feel more restrictive? So that's actually good. And I may do a poll on this. Would you rather me just post the stream link and say this is this date stream, and it be that simple, and to where at that point maybe that's more inviting, to where you can just bring your questions, whatever your chiller question is. It actually doesn't matter. um, in my head this format made sense initially, but I do find that there are people who have questions and who just don't really want to ask them because they feel it's off topic. um, yeah, I don't like. It's another one of those things. Like I could go either way with it. It's not really what I prefer so much as what what helps you the most. If having a dedicated topic makes you not want to ask some questions because you feel it's off topic, well then at that point it defeats a lot of what I'm trying to do here, and I should just remove topics altogether and just let's just get in and talk chillers. Um, eh, power of 2 with GPM increases. Yeah, Sterling, no issue on the the shorthand. The shorthand there on the messaging. I'm not quite following what you're saying there on the BT. Sorry, it's about uh, I guess water. Um, how do you know how much the GPM decreases with pressure drop decrease? Yeah, to the square root of it. I Let's see. So how do you know how much the GPM decreases with pressure drop. That's going to very specifically depend on the actual heat exchanger and its flow uh, designs. So, and I do want to clarify one thing. Talking water on these hydronic heat exchangers is talking refrigerant. Like they're directly tied into one another. So it's like talking air to the refrigerant circuit in a split system or an RTU. It's the exact same conversation and concept in theory. So don't I do find that we tend to think about these things as very separate for I think just because of our backgrounds. But in the same way, if we were talking a split system refrigerant circuit conditions, you can't have an in-depth conversation about that without discussing the airflow and the airstream. Like it's critical to that conversation. Water is the exact same thing here. They say pressure drop increases across the heat exchanger to the power of 2 with GPM increases. I've never heard that with a brace plate heat exchanger. Yeah, I've not heard that, Sterling. So I'm not familiar with that concept. That may be true to some degree. I would venture to say that may be true for a particular manufacturer. My gut tells me that would not be true across the board. So yeah, the different manufacturers, like it depends on how many plates, the gaps of the plates themselves. Like there's a lot of variables that go into determining what that flow curve looks like, and the pressure drop needed for that flow curve. And so I don't I don't think that would be that's an engineering level decision that they decide to make when they're designing that heat exchanger, more than that is a rule of thumb that everybody follows. Half the design pressure drop. So does it mean that my GPM is a quarter of the design flow? Yeah, I don't know. I've not seen, or I've never noticed the flow charts correlate that closely, if that makes sense. Like I've never, the variance of what that flow change means. When I was writing the flow procedure in the training program, it was actually some of the conversations I was having, and I was discussing this with some actual engineers who design equipment, and having the discussion of, hey, like, what are ways to calculate these things? Like, what other methods do we have to determine anything if we don't have the submittal data that has the flow requirements and stuff? And their literal answer was, there's not. Like, if you don't have the submittal data and you don't have the charts you need, like if you don't have that basic information, which is not always publicly available, unless you've got a flow sensor or a flow meter of some kind that you can trust. And that's the other issue with flow meters. They've got to be calibrated correctly. They've got to be installed correctly. Like, there's a lot of technicality into using a flow meter the right way. And so they're not as just drop and play as some marketing I've heard will make them sound. Okay, I do want to preface that. You have to be careful with those flow meters if you want an accurate reading that actually means something. Yeah, their answer is just, if you don't have that data, everything is a guessing game, and there's no set rules that anybody goes by. It's what they designed. And that's one of the things that's probably one area why chillers are so challenging on the flow side, is because they're not mass produced in the same way, especially water cooled centrifugal equipment. They're not mass produced in the same way that RTUs and other stuff is. Maybe the air cooled, I definitely see we have much better flow data on air cooled equipment that is far more just copy paste template designs. But that's just not true for a lot of these centrifugals and stuff. They are spec built many times. Now, we may they may not be that different from one another, and there are a lot of commonalities, but they're still spec built, and there's a lot of variation that the engineer, the team designing it at the engineering level or putting it together in their little software that they use. Like it matters a lot what they choose and what parameters they put in, and that changes things quite a bit. And so when we're trying to make precise determinations on flow and calculations, like it's just, that's probably one reason why they don't have generic flow charts like we would have an airflow chart on an RTU that they produce hundreds of thousands of at a time. Um, with the chillers, there's just far too much variance, and every chart would have to be just way too specific. I mean, you talk a hell of a book to make that true. That's what gets me with chillers. I always struggle because there are so many variables. You gotta guesstimate so many things. If you can't be sure about your GPM, then it throws off exactly right. Like that is the core issue, and it's been something that I've put a lot of time into at this point, trying to get my head around and try to find better solutions for us as technicians. Like what's something we could do? What's a better way to go about this? Like what tools do we have to do this better? It is why it's the problem that it is. It's why it comes up all the time. We haven't figured that out yet. We really haven't. So if the manufacturers would be willing to give us easier access to those databases, something like that, that'd be great. But they don't have any incentive to do that. Like for them, like there's no financial incentive for them to take that path and to create this database so that we third party can pull up our stuff for our machine that they'd really rather work on themselves. I mean, they're internal. They have that database. They're internal guys. If you work for the manufacturer, you can go in and pull that type of information. It's not that hard to do on their side. So it exists. We just don't have access to it. So, yeah, I mean, that takes, in their mind, it gives us a lot more ability to service our customers, which means that they don't have an opportunity to do it for us. The box just expects you to know, yeah, you dealt an approach, yeah. I mean, that comes down to the company, the management at that company. It's unfortunate, but anyway, I mean, like I said, I'm gonna do a poll on the subject thing, and just ask the community, like, is having a topic restrictive? And maybe we even try to do an experiment for a couple of streams where I'll still do the poll and ask, but I don't even if everybody says they'd rather pick a topic, maybe do a couple of them where I don't set a topic and just see how it goes. Because I've noticed far too many times in the comments as things are kind of rolling through that people either feel bad. I mean, like you, Sterling, you mentioned earlier yourself. You've been around here for a long time. Like you've been following. Like we've hung out for a while, right? And even you felt the need to say sorry. This isn't a refrigerant question, right? Like that highlights exactly what I'm talking about. Where this isn't. I think it's counterproductive at this point. I think I need to just go to, hey, let's have a general chiller Q&A. Here's the date and time. Show up. That makes a lot of sense to me. Anyway, I'll get a couple more minutes, guys. If we do have another question, I apologize for all the technical issues today. It's been a lot. I know the stream signal's gotten weak a lot of times. I had to restart the whole stream. Like it's been a lot today. I apologize. We had a beetle come join us. I've seen my screen glitch out a couple of times too, and I don't know if that's something on my end or y'all's end, or if y'all even if y'all noticed it on y'all's end or not. It's been a day. For example, today I had access to the specs order Delta, a design Delta and Delta PE, but I had half the Delta P and double the Delta T, yet the approach was very good, like 4 degrees. Well, that's the thing. Low flow is going to give you a good approach because it's low flow. Like the whole, yeah, exactly. Yeah. You would have expected a bad approach. No. So, because you would get a bad approach if you had high flow, but not with low flow. With low flow, like if that's all that it is, the water has so much time to transfer heat while it's going through there to the refrigerant that the two can equalize quite heavily. Now, you can get to a situation where the flow is so low where you start pushing the low suction pressure points, right? But the approach values will typically, like, you'll have a very low approach with low flow. And I here recently I've gone back through some of my much older stream or stuff I've done, and I see where as I have learned and grown as a tech, I've had to change how I explain things quite a lot. And I think this may be one of those things where I don't know that I explained it then the way I would now, the way I did a few years ago. And so, yes, low flow, you're going to have a lower approach just because of contact time. That water is able to make contact with that refrigerant at a long enough horizon that it can have a really low approach value. And now, if you had really high flow, then we have very minimal contact time and we don't get the heat exchange effectively. In addition to that high flow, because we're trying to make a leaving water set point, will force us to ramp our compressors a lot higher. And that high staging up more only forces our suction saturation down further, which increases our approach even further, trying to make set point, right? So high flow creates this very, very high approach condition, but low flow will usually have a very low approach to the point of then just tripping out on suction pressure or low pressure conditions. So that's been my experience with a low flow condition is you'll have actually like a phenomenal approach, and it's just because of contact time. So, okay, I think we will end it there, everybody. I appreciate you joining in. Had a lot of fun. MTT, make the time for your family, for your spouse, for your kids. They really need you. We're in the throes of the early stages of busy season. It's only going to get more busy from here. But make the time. Y'all take care. I appreciate your time.